somewhere while we were discussing the difference between trusses and frames. Today, the third class of this lecture series course on AM2200 Center Materials, we are going to learn a little bit more into what we need from engineering mechanics to SOM. So this is still an introductory part of the course that we're going through. I hope you can draw free body diagram for this member. If you cannot, it is drawn here in this slide. You can go through this slide and you can understand how the member free body diagrams are drawn. As you can see that each of the member has been freed separately. So this is a 2D member, two-force member, and you can see that the forces are collinear. Then this is also a two-force member, but there are three forces that are reacting on it. So you can see there are three forces, and all three forces are parallel in this case. All right, and then you have this member and then this member. So all the members have been separated and they are free body diagrams. What I have discussed about truss and frames are supposed to be written here. So I would suggest you, if I write it, good. If I don't write it, I have told you to copy it in the last class. Please copy and write them back here when you take these notes with you. All right, let's go ahead and discuss more things. Okay, in the last class itself, I told you there are a few things that are very important in strength of materials and probably in solid mechanics, as long as you are in solid mechanics. One of these are support and boundary conditions. Okay, so when you try to solve a problem or you want to design a structure, right, you need to solve a few set of equations. Those equations will be mostly ordinary differential equations in case of static problem, and will be a partial differential equation in case of dynamic problem, if you include flexibility in the system. Now, these ordinary differential equations or these partial differential equations, when you need to solve, you need to know the boundary conditions related to it. Okay, because you are probably trying to solve the deformation. Let's take an example. Let's take an example. It will help us to understand from the example itself. Okay, let's say we have a cantilever beam with us. I hope all of you know what is a cantilever beam. So this is a cantilever beam and this is its central axis, right? And the length is L. And it has a cross section, rectangular cross section, let's say, with the B and D as its breadth and depth. Now, when I say cantilever beam, I mean that one of its end is fixed. What is a fixed end? I'll tell that in a little few minutes later, but fixed end is it cannot move along x direction. Let's say my x direction is this. This is my y. Okay, so it cannot move along x, it cannot move along y, as well as it cannot rotate in xy plane. That means about z. Okay. None of these are possible at this joint, at this point. So that called a fixed point or fixed boundary condition. And if you see this corner, this another boundary of the beam. So there are two boundaries of this beam. One is this boundary A, other one is B, right? Now at A boundary, I told it's a fixed end, and B boundary is a free end, because here it can elongate. There is no one which is stopping it to elongate in this direction. There is no one which will stop it to deform along this direction, and there is no one which will stop it to rotate. So it can do all these three, and therefore it's a free end. Okay. So this is a fixed, this is a free. Now, when I say these boundary conditions, I mean that while solving for, so for example, you want to solve for deflections of the cantilever beam. You want to solve for it. How are you going to solve for it? Well, as I told you, you will get a ODE to solve it. We will show you this ODE in space later in time. Towards the end of this course, you will know what ODE is going to govern this, the motion of the system, the deformation of the system. Now, when you solve this ODE, you will solve it like something like it will deform something like this, maybe, or it may deform something like this, maybe, or it may deform something like this, maybe. I don't know how it's going to deform. But I will at least know this, that whatever its deformation is, this point is going to be at this point only. So whenever I drew a deformation, you see, I have drawn it from this, or maybe like this. It will not have a deformation that will look like this, because in that case, this point is no more connected to this, and it goes like that. So the point has moved up, and therefore it has violated the boundary condition that is attached to this point. So the choice of the deformation that the beam can have is determined based on the boundary conditions that it has, or support conditions. And therefore, boundary conditions and support conditions are very, very important to know while solving problems of solid mechanics. I hope that is clear to you. Okay, so let's go ahead and say what are the boundary conditions. So there are two kinds we say boundary conditions are. One is.
Hello, sir.
Yes.
Sir, the B end can be anywhere, right? Not at the same line.
No, it can. No, it can be anywhere. Yes, not on the same line, in the sense it will not be at the straight line, because it will bend like this, right? So it will move out from there, because the length has to be preserved. Okay. So it will not be along this line. It can go there, since it is free, it can go like this. If you give a moment, it can be like this, but this point will be here only. Okay. So
Okay, sir.
boundary conditions are two kinds. One is geometric boundary condition, we call it. Most of the time we write boundary condition as BC. Okay. Or we call it also displacement boundary conditions. That means the boundary conditions that arise due to geometry of the structure. Okay. When I say geometry of the structure, I mean connections. So this is the geometry of the structure. So the boundary conditions that arise due to geometry of the structure are called geometric boundary condition or displacement boundary condition. The next one is force boundary condition. The boundary conditions that arise due to given forces in the system. Okay. These are called force boundary conditions. Now there is a very nice relationship between them. We'll discuss about this relationship a little later. Right now, let us discuss this with an example. Okay, the same example I'll take now. Let's say the same cantilever beam is acted upon by a force F here or a P here. Okay. So now what are its boundary conditions? As I said, there are two boundaries to this beam. Right. So I write it here. Or if you want me to write it, I will write it in the next page here. There are two boundaries to the cantilever beam. Two, not red, boundaries, right? A and B. A we call it as fixed end, and B we call as free end. Therefore, we can call the beam as fixed free beam. And most commonly known as cantilever beam. All right. Now at fixed end, what do we get? If you see the fixed end, it's something like this. Right? The beam is fixed at this point A. So what are the conditions I'm getting here? Do you know what is the force acting at that point? You don't know, right? In the beginning, you don't know. You have to solve a few equilibrium equations to know what is the force acting at that point, right? So we don't know what is the force acting at that point. Therefore, let us write them one by one. Let's say AX is the force along X direction, AY is the force along Y direction, and A theta. Should I write theta? Okay, A theta being the moment acting at that point. Okay, or let's say let's write it better. It's F A X, F A Y, and M A theta. Okay, are these known to us? We do not know unless we solve equilibrium equations. So not known unless equilibrium equations are solved, right? Not known. Very good. What about deformations or displacement at those points? So let us write the deformation and displacement. The deformation displacements are maybe deformation along x, deformation along y, and rotation about xy, right? So we will call it rotation about xy. What do we mean by this? Deformation along x meaning it is moving along its direction. Deformation along y meaning it is moving along y direction. And rotation about theta anti-clockwise positive as this one, right? How much it can rotate anti-clockwise. So my conditions are boundary, so my coordinate are like this. This is theta, this is x, this is y. Always note that you have to give this anti-clockwise or clockwise. Okay. Now what about delta x at point A? Can point A move along x direction? I said it is fixed. So the point is fixed to that coordinate. It will not move. So I know it before solving my boundary conditions. So that's going to be 0 and known. What about delta y? Again, the same thing. Point A has been fixed to the coordinate system there, and therefore it cannot move out of that point, and therefore that also going to be 0 without solving the equation. And I said it's fixed again, so it cannot rotate also, right? If you fix something very tightly, can it rotate? It cannot rotate. Take a scale, take a ruler and fix it with one hand tightly and try to rotate. It will not rotate at that point. It will rotate at every other point. So that is also going to be 0. This is also known before solving the equation. Okay, very nice. No, we know everything about point A now. Anything else? Is there any question here? Any question here? No question? Over. You guys are very smart. That's great. Okay. All right. Now let's look at point B. What do we have at point B? Let's look at the forces, right? This is point B. Forces F Bx, F By, and M B theta, right? So these are the forces I have, and we are looking at a planar body, right? We are not looking at a 3D body, so we are looking at a planar body in plane. Okay. When I'm looking at in plane system, I have only 3 unknown forces, right? Fx, Fy, and M. For a 3D object, it will be Fx, Fy, Fz, and Mx, My, Mz, right? 6 of them. Here it is 3 only. Now, can you tell me, do I know force at point B?
No, sir.
We don't know force at point B?
Sir, what if there is external force? If there is external force,
Yes,
we will
yes.
know that.
Unless an external force is not present, then
If there is an external force, it will be given to you, right?
Yes, sir.
Then you will know it. Yes or no? If I give
Yes,
you an
sir.
external force here, let's say, for the sake of discussion, I give a force here P. So you know FBY is P, right? The equilibrium has to be satisfied at that point. Okay, so you know that. And if I give a moment at that point, let's say instead of force, I give a moment here, M. You know that this is going to be MB. All right, so that is known to us. So any external force is mostly known to us unless it's a design problem. Okay, so they are known to us. Even for design problem, we'll assume them to be known and then solve them. Right, so FBX is known to me, it is 0 currently. FBY is also known to me, 0 currently. FB is also known to me, 0 currently, right? All these are known to me. What about the deformations? Okay, I have to name them as A here, and A here. So I'll write here as delta Bx, delta by and delta b theta, or xy I wrote, right? So it should be xy or theta. Sorry, theta b x. What about this? Do I know the displacement or deformation at point B? I don't know unless I solve it. Okay, so that is not known to me. Same thing for deformation, transverse deformation, same thing for rotation at that point. All are unknown to me. Okay, very good. It's a very good problem. And now let us look at it. If you see at point A, please note few things. Point A, all your forces are unknown, and therefore your force boundary conditions are not known. Whereas your deformation or displacement boundary conditions are known to you. They are all zero. If you look at point B, your force boundary conditions are known to you, they are given, whereas the deformation boundary conditions are not known to you. So note this. So therefore, what I'm going to tell now, please pay attention to it. It is always that either you will know force along a particular direction at a particular node, or you will know the geometric boundary conditions at that particular point along that particular direction at that particular node. Okay, you will not know both. You will know either one of them, and you will be solving the expression based on what is available with you and get the unknowns that are not available. Is that clear? I will repeat again. Okay, given a point, given a direction, you will only know either the force boundary condition or the geometric boundary condition. You will not know both. So you'll start solving your expressions based on what is given and find the unknown. One example was this. As you can see, that these are all force boundary conditions. These are called force boundary condition. Force boundary conditions. So B and C. And these are geometry boundary conditions, G, B, C. Right? Same goes here. And if you're not satisfied with this, let us give another example. No. But please remember this example. I'll not spend time again to explain these things because it's going to take a lot of time. Yes?
Sir, I had a doubt, sir, for the free end.
Can you tell your name first?
Sorry, sir. My name is Akhil, sir.
Akhil. Okay, Akhil. Tell me. Yes.
Sir, for the free end at B, so we say if Bx is 0, if By is 0. So can we say that the net force at the particle B is 0?
Net force at point B, yes, it's 0, no?
So then, like, would there be some kind of internal force applied by the point just adjacent to B on B to, keep it in the rod?
Yeah, you are very right. So the point just before B will have some force, but not the B. Because if you have some force at B, B is not going to transfer it to anyone. There is no one there, right?
Correct. Yes,
Unless
sir.
there is another boundary condition here, B is not going to have that force. And therefore,
Yes,
if you know that cantilever beam, if I draw, and if you might have drawn its SFD and BMDs, right? If you
Correct.
see its SFD, how does it SFD look like? SFD is like this. It suddenly starts from that point, right?
Yes, sir.
And the BMD is going to look like this. Here also, it suddenly starts from that point, just after that point. So at that point, it's 0. It will start after that.
Yes, sir. We start from 0 at that point. So okay. But of course, there'll be an internal force acting on it, sir.
Not at that point, just before that point.
Just before that point.
Yes. That point, there won't be any force because that will violate the boundary conditions. In fluid mechanics, if you have done, you will see that there are shear forces acting on the boundaries, right?
Correct, sir.
Right. That will not happen here unless there is a shear force acting on the boundary.
Oh.
If I give a shear force here, then only I will have a force here.
Yes, sir.
Otherwise, not. Okay.
Yes, sir.
Is that all right, Akhil?
Yes, sir. Thank you, sir.
Okay. Now let's go to the next example that I was about to take, and to make sure that you understand what are boundary conditions and what are the things that will be available to you. So when I'm telling this, please make sure that when you see a problem, you see from this perspective, what are the boundary conditions available to me, whether these are geometric boundary conditions or the force boundary conditions. If there is geometric boundary conditions are known to me, there are the force boundary conditions that I have to find in that case. Remember, if the force boundary condition is not known to me, then I have to find the geometric boundary condition there. Right? It is always true. You have to do that all problems that you learn. Now let's look at a single simply supported beam. Okay. Now this time I am not going to solve it. You are going to write it in the chat, or if you want, you can just open up and say, not a problem to me. I have a force here. All right. Can you now tell me what are its boundary conditions? First thing is I have to name point A here, point B here. I have only two boundaries, point A and point B. All right. So point A, point B. Now tell me the boundary conditions. What are the forces and moments acting at that point A, and what are the forces and moments that are acting at point B? This is also a planar body, right? It's also a 2D body. And its coordinate axis is also like this. I always take anti-clockwise as positive. Unless I mention it, it will always be positive anti-clockwise. Okay. All right. So please start doing it. Point A. What are the force boundary conditions we have? Force boundary conditions.
P/2s.
Again, you are solving the boundary condition. You are solving the equilibrium problem, right? You're taking moment and doing it. So let's look at the values. Let's say if AX, if AY, and the next one is what? M A theta. Similarly here, if force boundary condition, it's not free body diagram, okay? Don't mix with free body diagram. It's a force boundary condition. Let me write it. Force. Same thing here. This is F B X, F B Y, and F M B theta. And let's also look at geometric boundary condition. Geometric boundary conditions. Okay. What do I have? Delta A X, delta A Y, and theta A X Y. Similarly here also, delta B X, delta B Y, and theta B X Y. When I say a simply supported beam, what do you mean by this boundary point? Let's not give any force, because if I give a force, you will start doing this equilibrium. You cannot get out of that equilibrium till now. You have to leave that behind. It's gone in engineering mechanics. So there is no force. There is no force doesn't mean there is no boundary conditions, right? Boundary conditions still there. As long as support is there, boundary condition is there. And if there is no support in the free case, there is another boundary condition that I told you. What is the boundary condition for free case? It's all shown here. The boundary condition free case. Now here, for a simply support case, what do we have as a boundary condition? What do we say a simply supported structure as? Or, when we say simply support, what do we mean by a simply support? Can you tell me? Anyone? If I join a link with a simple support, okay, let's take a different color. If I join a link with a simple support, let's say like this, what are we going to tell about this structure? You're going to tell me.
Can't displace.
Hello?
It can't displace, sir.
Yeah, can you tell? Yeah, good. Very nice. Thank you very much. So you will say me that delta x is not possible. Delta y is also not possible. Okay, but what about theta?
That-
It's possible, right? It can rotate. You give a slight moment, it will start rotating, right? Hello? Someone please answer yes or no.
Yes, sir. Yes, sir. Yes, sir.
Yes,
Yeah,
yes, sir.
Good. You good. So I know the boundary conditions then. So I know delta x ax going to be 0, delta y is going to be 0. These are all known. This is not known. Okay. Now look at the forces. At this, if you have this support, when you release this and make a free body diagram, what do you draw? You draw two forces here, right? Do you know why you draw two forces there? Not another moment. Because if I pull that rod, towards x, the rod is not going to move towards x at that point, this point. At this point, the rod is not going to move along x. Therefore, somebody is holding it. And that force is generated by this support, and that is this one. Similarly, if I pull that rod towards up, the rod is not going to move up because somebody will hold it towards down, right? And that is this force by the support. But if I try to rotate it, what will happen? It will rotate, right? Why? Because the support is not resisting any moment. It doesn't resist any moment. Simple support does not resist any moment. Please remember this. And therefore, the moment condition is 0 here and is known. Simple support does not resist any moment. Okay, but the forces will be resisted, and therefore this is not known to me. This is not known to me. Now look at this pair. Very interesting pair. Force along x direction at A is not known, but displacement is known. Force at A along y is not known, but displacement is known. Moment at A is known, slope is not known. Okay, so as I said last time, the same thing valid here, that you will either know at a point, given a direction, you will either know its force or you will know its deformation or deformation boundary condition. Remember that. Why moment and moment and theta comes together? Because they form the energy. Force and displacement also forms the energy. Okay, therefore they come together. Force is always related to displacements and moment is always related to slopes. Okay, similarly for this boundary condition at B.
Sir?
Yes.
Sir,
Yeah, please carry on.
One small doubt, sir. Here, this either force boundary condition can be known or geometric boundary condition can be known as a point, no, sir. That
Yes.
is only when there is no external specification like what all forces are acting. Am I correct, sir? Like,
No, even in that case, this is true whether there is a force acting or not.
but if there's a force acting, we can find Fax and Fy minus.
Yeah, of course, but you have to solve the equilibrium equations. I'm talking about before you solve it.
Okay, sir, fine, sir. Yeah. Okay, sir.
Okay. All right. So before you solve, you have to do this. So when you solve it, you can get the boundaries forces, right? But if I have to solve internal forces, you need these boundary forces to solve the internal forces. Okay. So you are going into one step by another step for solving the equilibrium equations. And then maybe the differential equation of equilibrium you have to solve, which will come later. So point is, before you solve, when I give a structure to you, these are the things that should come immediately to your mind. Okay, clear? Same thing has to repeat here. Not known, known, and 0, 0, 0, known, and not known. All right. So please write it down, whatever I said. This is very important for you to understand how we go ahead and solve our problems. Yes.
Sir, for a roller joint, we know there is no force along the x direction, right?
Yes, but yeah, understood. But since It's because of common mistake we make, that we assume that there's the vertical load. So at point B, it can move along that direction, right? So the force will be 0, of course. There is no force that it resists, and therefore deformation can be there along that direction. You're right, very right. Who was that?
Archish, sir.
Archis, yes, you're very right. Generally, when we draw a simply supported beam, we assume that there is a transverse load. But that's not true. It may not true that always there has to be a transverse load. There can be a axial load also. Okay, so if there is an axial load, whatever you said is correct. A general condition is this. Thank you, Archis. Okay, now these are all discussed here, and I have written those things whatever I discussed. Okay, so please go through them. And these are the supports that you can get. This is a roller support. When I say it's a roller support, it means force is along both the direction. A roller support doesn't mean that it can go up and move. No, we don't differentiate that unless we tell it properly that there is a sliding mechanism. So I hope that you know this kind of. So for this kind of roller force, there is only one force that is unknown to you. Other two forces are 0. So these are known boundary condition. And similarly here, there is sliding. So sliding also gives you force only along one direction, not the other direction, because it's free to move. So it's very easy to understand. Suppose there is a room, a big room or a small room packed with people. Okay, and suppose you are one of them, and you are trying to move towards the gate. Okay, towards the exit. You are trying to move towards the exit. You will not be able to move if there is a lot of resistance from other people to you. Right? You have to overcome that force to move. Okay, that means as long as there is resistance, there is a force, your motion is 0. Right? But if the room is empty and there is no people there apart from yourself, then you can easily go to the exit, right? And there is no force acting on you. Therefore, when you have a motion, there is no force that is acting on you. So either the force will be there to make sure that you have a 0 deformations, or you will have motion to make sure that there is 0 force. Now apart from this, there can be conditions where can be some deformations can be there, some forces can be there. We will solve those kind of problems. But in general, this is the condition that is going to be satisfied. Some cases, for example, I can give you one example itself right now. Suppose I have a cantilever beam again, and I give a spring here. So now see, in the previous case, we said the forces at this point is 0, right? Force at this point is 0, but now it won't be 0 because there is a spring attached. So spring will give some force. And we said it's free to deform, but now it's not free to deform because the deformation will depend on the spring. So this kind of conditions will also come. As and when these kind of conditions come, we'll solve them as required. Okay, we'll show you how to solve them. Okay, but apart from that, most of the conditions, majority of them will be whatever I said. Okay, this is for planar system when you have a hinge, right? A hinge or a rough surface. Why did I go? For a rough surface or a fixed support. For a fixed support, there are 3 unknowns, 2 forces and a moment. Okay. Now you can say again, sir, I can solve these unknowns with equilibrium. Yes, you can, but they are unknown. That's why you are solving with equilibrium. Okay. Okay. Support for 3D system is also same, similar. You can go through them. Yeah, a practical consideration, the support look like this. This is a simple support or a roller support. This is a simple support with a hinge. You can see it cannot rotate. Sorry, it can rotate about this axis, right? But it cannot move along this direction or along this direction. Oh, sorry, along this direction, neither along this direction. Similarly, this is called a fixed point. So you can see they are fixed with a gusset plate or with maybe with nuts and bolts. Okay, and therefore it can neither can move up and down, cannot go out, neither can rotate at this point. Because if it tries to rotate, these portions are going and these portions will come out, right? That is not going to be possible because they are fixed here. As long as, so we'll assume an ideal fixity. So as long as the fixity is ideal here, that means complete fixity is available, it will not rotate. This is a fixed support example. Now, when you have a structure, there are the forces on a structure are separated for ease of solutions mechanics as two types, external and internal. All right. Now, for general cases of problem analysis problem, this will be given, and this need to find out. For a design problem, it will be quite the opposite. Internal forces, maximum values of internal forces will be given to you, or you can find them easily. You need to find the external force from the various equilibrium and constitutive laws and other equations that are available to you. Okay, constant equations, everything. Right? So generally there are two kinds, external and internal. For an analysis problem, let's assume that external will be given and you have to find internal. Why do you need to find internal forces? Now, when you have a structure, all these are drawn here. When you have a structure and you load it from external side, right? The structure will try to release that load to the ground, to the foundation, or to different parts of the body, of the structure. I can draw an example here, a better example, that let's say that the building that you are in is something like this. This is the column of the building. Right, this is another column of the building. Let's say I'm drawing only one bay and there are 3 floors. I don't know which floor you are staying. Let's say you are staying here. There is a table here, right? And you might be sitting here with your computer and all. Okay. Now, when you are sitting here with the table and your other items, you're giving some load at this point, right? Structurally, I'll design it as a point load at that point. Or maybe a little bit of distributed load, but let's say a point load is good enough. Okay, this is how I'll design or I'll analyze. And when I put this load here, this load has to transfer to this joint and this joint, and then it has to move down to the ground foundation and release there. The load has to be released there. Okay. So what happens between this joint and this joint when this load comes in? Let us say that we model it as a beam. Generally we model it as a plate, but let us for the sake of simplicity, as we don't know, let us model it as a simply supported beam. It won't be simply support, it will be a fixed beam or a fixed plate based on the fixity here. But for the case of simple discussion, let us put this load here, and that's what we have. So this load what will it do? It will deform the structure. Structure will deform like this. But it will go by its boundary condition. So it will come back to this point here and also this point, because deformation at those points will going to be 0. But it will bend like that. Okay. Now, why it's bending? The structure is trying to release the load through this to the support and through this to the support. While it is releasing the load has to transfer from each of the particles or points that are here inside. Right? So what it will do, it will try to push fibers against each other. Okay, the structure will be, let's say it's a wooden structure, there will be a lot of fibers in it. It will try to push the fibers against each other. And when it tries to push the fibers against each other, there is a force that is generated between the fibers. That force is called internal force. Okay, so this P force will move internally as an internal force because that is generated between the fibers, between the layers of the beam that we have. And therefore, it's called internal force. Okay. Now, when I say internal force, every material or every structure will have a maximum tolerable capacity, right? So if let's say, take an example, take yourself as an example and put some load on your head. Okay, you keep on putting some load. After a certain time, you will no longer be able to bear that load, right? It will start crumbling, it will start failing. Similarly here also, if I keep on increasing the load P, after a certain time, this load P will start breaking these, the fibers that are between each other, they will start breaking because they cannot take any more the load. So that is the maximum load it can take. In a design criteria, you have to find from that maximum load, what is the external load that it can have. Okay, in this case, you know that P, you can find out what P is here. So you know what is the shear force here, right? And what will be the shear force here, right? This will be, let's say if it is A and B, so these are the things that you should know. If this is A and this is B, then this should be P into B by L, and this should be P into A by L, right? You know that, you have to remember those things. So you can see that different direction, it has different load. Therefore, this side of the structure will have lesser load. I have, the diagram is not in scale. Right, diagram is not in scale. So let me draw the diagram in a scale. So the shear force diagram is going to be like this. Right, this will be B by L, this will be P A by L, right? So you can see that this side of the structure carries more load, the elements here or the filaments here or the fibers there will carry more load than this side. Okay, and therefore there is a prone to failure on this side far before there is a failure on that side. So this is the shear force diagram, which is the internal force. Now shear force acts vertically. Okay, but when the structure bends like this, okay, when it bends like this, it creates a moment also in it. This is called bending moment, and bending moment actually acts. If I draw a section here, section AA. So if I draw a section AA here, right, this is the beam with the section AA. It acts as an axial load on the structure. So there will be one side that will go like this and one side that will go like that. Okay, so this actually forms the couple, and that's actually your bending moment. We'll deal with this more in the second part of this course, but for for your understanding, a bending moment or a bending force or bending stress is an axial stress. It acts along the axis of the structure, but they form couple, and that's why they form a bending moment. So this is an internal force. Now, structure or material fails not due to external load, but due to internal load. But as I said, the fibers will fail because the force that they are carrying internally, not due to the force that is externally there, because external force will be divided into different values when they go internally. Okay, so the fibers here will fail because of a load that is PA by L, not because of P. Well, this PA by L indirectly depends on P, but the failure is because of this, not because of that. Okay, that's an internal force and external force. Now, internal external force. Yes, who's this? Hello. Okay, I'll stop in a minute now. So there are a few bending moment diagram and circular diagram given here. I'll upload these notes today. I did not upload last class, so you have to solve this bending moment and shear force diagrams yourself and see how can you quickly draw them. Always try to draw quickly. We'll talk about static equilibrium in the next class, and with that, we'll start our strength of materials. Thank you very much. I'll stop here. If you have any question, you can quickly ask it.